So definitely from looking at some of these computations here, it certainly seems that there's a pretty close connection between the singular value decomposition and the singular value expansion. And it's not purely coincidence. And these last slides sets up some relations that explains this connection. So it's nice to know, because then from now on we can look at the singular value decomposition and we can be sure that it actually tells us a lot about the singular value expansion. It's not just that we can hope it does, it actually does. Okay. So we get some theory that supports that, and in fact this theory also tells us that if we want to compute the approximations to the singular value expansion, then we can do it by means of the singular value decomposition. So two things at the same time. All right. So in these last slides here, I assume that we are using a Galerkin method with orthonormal basis functions to discretize the problem, because then we can do this theory here. There are also some papers about similar relations when you're using a quadrature method, but let's do it for the Galerkin method here, because then it's not too complicated to go through the arguments here. All right. So you choose your basis functions, the phi and the psi functions. You discretize your kernel to obtain the matrix A. And then the theory, I'm not going to go through the theory, I'm just summarizing the results of the theory. Again, you can look in the book to see more about the theory. But then we can prove that the singular values of the matrix, they will actually converge to the singular values of the function k as n goes to infinity. And n is, of course, the size of the matrix, and the matrix is n by n. And we have similar results, of course, when we solve, for example, differential equations, that as the system gets bigger and bigger, we have this kind of convergence. So that's very nice. So what about the singular functions? We compute singular vectors. Is there a relationship now between the elements of the singular vectors and the singular functions? Indeed, we just have to be careful how we define that. Right. So let's see. There's a sum here over the psi basis functions. And then there are some expansion coefficients here. And of course, these are the elements of the U matrix from the singular value decomposition of the matrix A. And you see we sum over I goes from 1 to n, while j is fixed, because we have fixed j. So really what we do is that we take all the elements of the jth column of the U matrix. Okay, that's what it is. So we take the elements of the jth singular vector and we multiply them to the expansion coefficients here, blah, 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 blah. So of course we get a function. When we add functions, we get a function, and we call that uj n, superscript n there, and we can do that for j from 1 to n. And of course, we can do the same thing here. We can define some functions vj, superscript n, by taking the phi function and the element of the V matrix. Right, so that defines some functions. And sure enough, these functions that we just defined using the singular value decomposition, they converge to the actual singular functions from the singular value expansion. Yeah, man, isn't that nice? I think that's totally nice. And one more thing here. If we also discretize the right-hand side by means of this Galerkin approach, then these expansion coefficients of the right-hand side in the SVD basis, they are identical to inner products of these approximate functions over there in function space, and they actually converge to the true expansion functions as, again, the as n goes to infinity, as the problem gets larger and larger. So everything converges. Isn't that nice? Right. So really, when we look at these Picard plots, we are looking at matrix quantities, of course, but for large values of n, it's just like looking at the real thing. It's like looking at the singular value expansion and stuff related to that. So that's totally nice. So that tells us something about how we can do that. And there's more, because anyone interested in computing approximations, you know that one of the first, well, the first thing you should ask yourself or your teacher is, does this converge? Right, because if it doesn't converge, it may not be so useful. Okay, so here I'm summarizing that we do have convergence. But then the second question you should ask is, how accurate are these approximations when n hasn't gone all the way to infinity yet? Okay, so here's a slide about that. So we have to define stuff. We have to define a norm of the kernel k. K is a function of two variables. So we have a double integral right there. So that's a 2 norm squared. It's defined like that. And the corresponding quantity for the matrix would be the Frobenius norm. And so we define kind of an error measure there, delta n squared, which is the squared norm of the kernel minus the squared norm of the matrix. Now, I'm not going to prove that here, but it turns out that this guy here is always smaller than that guy here. Okay, so it makes sense to compute this guy. And then we have these results here for the singular values. The first equation tells us that the difference between the singular values of the kernel and the ones from the matrix are always, the difference between those two is always bounded above by delta n. Okay, so that's an upper bound for how the error in the computed singular values. So that's one thing we see. The other thing we see from that one is that the since this difference there is we can prove that's greater than or equal to 0, that means that our computed singular values are always smaller than or maybe equal to the true singular values. Right. They're always they're one-sided. This is something very fundamental about projection methods and Galerkin methods, because you have something that lives in infinite dimensions and then you project onto a finite dimensional space. So it's related to that fact that your approximations will always come from below. Okay, so that's a nice quantity. The second equation right here tells us that when we increase the size of the problem, if the size of the matrix goes from n times 1 to n plus 1 times n plus 1, we get even better approximations, because the new approximation here from the slightly larger problem is squeezed in between the previous value there and the true value. So we have monotonic behavior of these approximates of these singular values. They always get better. So that's kind of nice too, isn't it? And then we can also say something about errors in the functions. And I'm just stating the result here, basically. Okay, so the largest error here, either in the left or the right singular function, here is bounded above by that guy over there. Right. Again, this is actually known stuff from things behave in the same way for differential equations. And you'll see an interesting thing here. If the first and the second singular values are very, very close, then you have may have a large term here on the right-hand side. And that's because from the numerical point of view, it may be difficult for that numerical method to distinguish between the first and the second SVD component. And yeah, that's what you learn from that. So anyway, we have similar results for all the singular functions, but it gets much more complicated. I'm not going to go through that here. So we certainly have a very nice relationship between the singular value decomposition and the singular value expansion. Right. 3 more slides and then we are done, because I do want to say something about noise. Okay? And I'm not talking about noise from the construction work over here, but the noise in our data. So just to set up here, because we're going to be using that through the rest of the course again. So we'll always have a linear system of equations with noisy data and noisy right-hand side. Right? And by that I mean that the given right-hand side is the sum of an exact right-hand side plus noise, and the exact right-hand side is equal to A times an exact solution. So if there were no noise, it'll all be good, but we have the noise. And of course, if you solve a system with a noisy right-hand side B, you will never be able to compute X exact, but we hope to compute an approximation to the exact solution. So that's the name of the game. And to do that, we just have to say a little bit about the machinery here. Underlying that, here's a little bit of statistics. And if you have taken courses in statistics, you will be able to say much more than I do here. But yeah, there's some useful relations here. So for example, if we compute X as A inverse times B, okay, assuming that A inverse exists, then you can relate the covariance matrix of the solution to the covariance matrix of your right-hand side B. So remember, the covariance matrix here says something about the variations in the noise in the data. And this tells us about the variations in the solution. And you can see they are related in this way here. That's a basic result from statistics. And if you work with the least square solution instead for over-determined systems, you have that one there. So man, it looks complicated, but it just it tells you how basically how errors in the right-hand side influence, give rise to errors in the solution, or variations in the data give variations in the solution. And the bad thing here is that for the square systems, you multiply with A inverse, and you and also multiply with A inverse transpose, and A is this very ill-conditioned matrix, So we can actually expect that even small errors in the right-hand side, they will blow up into much bigger errors in the solution. Of course, we knew that already, didn't we? For example, from looking at these plots here. Yeah, errors are blowing up here. So we already knew that. This is just another way of stating the same problem, just in a different language. Right. In basically all the numerical experiments we're going to do in this course here, we'll assume that we have white noise. So the covariance, and that noise is uncorrelated with the exact solution. So the covariance matrix for B is identical to the covariance matrix for the noise, and we assume that that is a scaled identity, right? And eta squared there, that's the variance of the noise. And eta is the standard deviation of the noise. And again, if you have taken courses in statistics, you might just get a little bit confused because statisticians, they always use sigma for standard deviation. So why don't I do that? That's because I already took sigma for the singular values, so I don't want to write sigma here again. That's too confusing, so I use eta here instead. Eta is my standard deviation of the noise. And then, of course, we can see that the covariance matrix for the solution, or the least squared solution, is eta squared times that inverse matrix there, again telling us that for ill-conditioned problems this noise will blow up, and we don't like that. And the very last slide here again connects to stuff that we already discussed previously today, namely how these errors in the right-hand side manifest themselves. All right? So we look at the right-hand side coefficients in the SVD basis, and they are, of course, equal to the exact coefficients and the noise coefficients. That's precisely what we had over here. And, of course, for the small indices, when these coefficients are larger than those, we can approximate them by these. And for large indices, we can approximate these coefficients here by the noise coefficients. And that's what we already saw, but now I state it more precisely here in terms. And again, you can see that it's those guys here we want, and we can actually see these guys here in the first SVD coefficients, and we want to get rid of these SVD coefficients. Right, so this is a very good place to stop now. I have lined up, so we are ready to do regularization. Now we have identified that the singular value decomposition gives us a lot of important information, and it tells us basically who are the good guys and the bad guys, and then from now on we're going to be fighting the bad guys by means of regularization. So we do that from next week on.